Okay, so in this very short lecture, I'm going to just go over the center of mass, how you would define it, how you calculate it, and give you an example. This is an important aspect of being able to combine objects within a system, and then you can calculate the entire system's position as its collective mass and its location of all of those mass points. You divide that by the total mass of the system, and you have what's called the center of mass. It's a weighted sum of all of the positions of the particles. And so, to write that down, the center of mass describes the position points of a collection of particles within a system. And if all of those points are mass points, so if we imagine we have some series of mass points, and we know all of the locations of all of these objects, we can easily write down the vectors that describe the positions of the centers, R1, R2, R3, R4, and R5 of all of these points. And knowing something about our coordinates and knowing something about the masses, M1, M2, M3, M4, and M5, I can determine where the center of mass of this grouping of particles might be. And it could be somewhere, for example, let's say right here. If they're all equal massed, perhaps it's sitting at this point along this vector, R, center of mass. So let's figure out how to calculate that. So R center of mass is going to be equal to, well, it's the weighted sum, like I said, M1 R1 plus M2 R2 plus M3 R3, well, I'll just do 4, plus M4 R4 for this example. I'm ignoring R5 for a moment. And what I have to divide this by to get the dimensions correct, I have masses times positions, and I'm going to take this over M total. What I want is a position vector, and so again, this is the weighted sum average. Each one of these divides by the total mass, which means that I have this as, so M total is the sum over I to n of all of my masses, which in this case is M1 plus M2 plus M3 plus M4. So that's the sum. Now, to do this in practice, you would need an example. So let's do a quick example. And the nice thing about having the center of mass is now I can utilize that vector to calculate things like velocity or momentum of my system. And so a very straightforward example is the following. Let's actually give this real coordinates. 1, 1, and this one is okay, 5. Okay, so I have one mass here, and I have another mass, let's see, M2, that is here. Okay, and I would like to know the center of mass of this system. The center of mass of this system is going to be, well, the weighted sum average of all of the points that connect the centers. Okay, now it's a little confusing. Let's do this a little bit better. I'm sorry. Here's my first. Here's my second. And I'm going to connect the centers along this line. This is mass 2. This is mass 1. Okay. And so, our center of mass, position of the center of mass vector, is going to be equal to, well, mass 1 times, and this is x and y, x1, y1 plus m2, x2, y2 over m1 plus m2. And if we put in some values, let's say mass 1 is equal to 10 kilograms, and mass 2 is equal to 3 kilograms. My positions here are 1, 1, and 7, 4. And so using these values, I can very quickly find that the center of mass vector is going to be equal to, well, 10 times 1, 1, plus 3 times 7, 4, divided by 13, which should in the end be equal to our center of mass, which is equal to 2.4, comma, 1.7. And in my coordinates, so 2.4, that's 2.4, it's about right here, and it should be 1.7. So it's along the line that connects their centers. So our center of mass is this vector here, and it's at this point along the value there. So we can use this point. If I think about what I've drawn, I have 2 points. Here is a mass. Here is a mass. I have a line that connects along their center. And the center of mass between those 2 points is always going to be there. So if I throw this object through the air, even give it a spin, give it some rotation, if I only paint a little glowy part here and turn off the lights, what I'm going to see is the trajectory of this object is going to be the trajectory of the center of mass. And so no matter what I do to the system, I can always balance it here. And if I throw it, if I launch it, if I do anything to it, the motion point that I can calculate all of the velocity, all of the momentum of this object, of this system, if they're actually connected along this line, if it's really a rigid line, is going to be right at this point. So that's a nice thing. So I can write that the center of mass, the velocity of the center of mass, v center of mass, is just equal to the derivative of r center of mass. And likewise, I can write that the p of the center of mass is equal to the mass total times v center of mass, which is a really nice thing to be able to have. And that's going to be the p of the system, right? So every mass total, this is the sum of all the masses, each mass times the velocity of the center of mass.